Welcome, Sam. Hello. Hello. Welcome, Sam.
Hello. Sorry, I think I was muted.
Yeah, it's visible now.
Oh, great. Hi, thanks a lot for having me.
Fine. Rakshana, are you
Can
there?
you see can you see my slides?
Yeah, we can.
Perfect.
Rakshana,
Yeah.
hold on, Sam, once again. Rakshana, are you there? Rakshana? Rajeshwari, ma'am?
Yes, sir.
Ma'am, can we start?
Yeah, yes, sir. Once again.
Okay, ma'am.
Happy morning to all the energetic participants. It is a great pleasure to welcome you all the 5-day International Faculty Development Program on recent trends in applied mathematics. Our management encourages us to maintain strong links with the teachers community. We also appreciate our Dean Sir, Dr. A. Vishwanathan, for his great assistance. I would especially like to welcome my friends and colleagues and the speaker of today, Dr. Samuel Johnson, lecturer in applied mathematics, University of Birmingham, UK, who has kindly accepted our invitation to share his wisdom and insight. Finally, a warm welcome to all the participants around the world. Hope you all are safe and sound at home to learn continuously, and we assure you that you will definitely be benefited as we have amazing speakers lined up for you. I wish you all a very fruitful discussion today. Happy learning. Now I hand over the session to Mr. Sham sir.
Sam, you can continue.
Oh, okay. Sorry. Here I am. So, well, thank you very much for the invitation, and to Senthil Kumar for getting in touch. And thanks everyone for coming. So I'm going to talk to you today about complex systems, and in particular about a very common representation of complex systems, which is as a network or graph. And here you have some pictures of few networks, and these are just collections of nodes, some of which can be connected by an interaction of some kind, which we call an edge. Now, often these interactions are symmetric and they're represented with just a little line, but when there's some kind of directionality, so there's some asymmetry between the interaction that goes in some sense from one node to another, not necessarily in the opposite direction, then we might use an arrow, and this would be called a directed network or a digraph. And so I'm going to talk in particular about the importance of directionality in complex systems in general, and some of the effects that arise from the fact that these interactions can be directed. These networks, by the way, are inferred from some recordings, some EEG recordings of people's brain activity. So each node here is actually an electrode. So what are complex systems to start with? Well, there are many different definitions, but I quite like this one of the whole being greater than the sum of its parts. Not that that necessarily means very much. So people often think about complex systems as those in which many elements interact with each other somehow. But let's think, for instance, of a gas. So a gas like the air in the room where I'm sitting, let's say it's at thermal equilibrium. That's made up of many quintillions of particles, all of them moving about and sometimes interacting with each other. But if you want to know, for example, the pressure on the wall or the relationship between the volume and the temperature, that kind of thing, you don't actually need to take into account any complex behavior that emerges from these interactions. In fact, you can just think about one particle and say, well, the pressure is the sum of the force of all the different particles that might hit this wall, for example. So in some sense, this is just the sum of its parts. So this is not a complex system. However, similar molecules in a slightly different situation can give rise, for example, to these snowflakes. So here we see something much more interesting on a macroscopic scale. We get these funny shapes. Many different kinds of shapes can emerge. It's not at all trivial to just thinking about molecules of water, say, to predict what kinds of shapes are going to emerge. These shapes come about because at a microscopic scale, the molecules of water have a shape, and they can only stick together in certain ways because of the laws of quantum mechanics, like Lego blocks. And the symmetries at this small scale end up manifesting in this interesting way on a larger scale. So that would be a complex system, perhaps one of the simplest complex systems. That's what I mean by complex. And I'm going to use models here. I'm sure you all use models for various things. And I just want to ask this question, what are models for? Because sometimes there's plenty of confusion about this point. So it seems to me there are two kinds of models, if you like, but you could also say there's a spectrum, really, of realism in some sense. So on the left over here, we have an example of a model which attempts to capture everything that we can, or everything that we really need to, about a very specific system. Say you want to operate on someone's knee, you need to have a good model of that particular system to get it right. On the other end of the spectrum, we have models like this Ising model that physicists use to understand phase transitions. And this is not supposed to be very realistic. So no one thinks that atoms are particularly well described by arrows that can just point upwards or downwards. But that is actually what we need to think about if we want to understand why we get a phase transition between paramagnetism, where the magnetic moments of the atoms are not aligned with each other, and ferromagnetism, where they are. So it's useful in that sense. And then there's a whole range of things in between. Now, I tend to work more with the models of the kind that are on the right. So I'm usually interested in finding the minimum ingredients that I need to explain some phenomenon of interest. So this is like if you're interested, for example, in why do cakes rise when you put them in the oven? Well, you might want to find that the minimum ingredients are probably water, baking powder, and flour, for example. And that explains how it rises. And then you submit that to a journal, and typically the referees will tell you, oh, but why didn't you put chocolate in it? Why didn't you add Smarties and candles and things? And you have to try and explain, well, it's because I'm not trying to make the best cake ever. I'm trying to understand why cakes rise. So it's a better model if I only have the minimum ingredients than if I put all kinds of ingredients in, and then I don't know why it's risen. However, there's a danger with this approach that you miss something because some ingredients really do make a big difference. Like, for example, tequila. If you add tequila to your cake, this may have many advantages in various different ways, but it may actually affect that property you're looking at. So if you add too much tequila, perhaps you might kill well, actually, you probably wouldn't in a cake because it's baking powder, but say you're using yeast to make this cake rise, then you might stop the cake rising. And so not taking into account the tequila could have given you an erroneous understanding. And so because I tend to be on the right side of this modeling, often I find people who say to me, oh, when you think about networks, what's the point in taking into account the directions? It's just a bit of a trivial added ingredient. And I'm trying to make the point here that actually it's more like tequila, and it really does make a big difference in some cases. And in fact, there's a kind of analogy with this Ising model over here. So when you have directions on your edges, some networks will see a bit like paramagnetic networks in that these edges the directions of these edges are statistically independent of each other. But some networks have a kind of global alignment that's a bit more like an ordered phase in a spin system, where at least some of the edges are to some extent correlated, and this leads to interesting phenomena. So here's some example of networks, and this is why we often represent complex systems with networks. Sometimes the complex system in question, for example, a brain over here, is made up of many neurons, many relatively simple elements, perhaps, that interact with each other. You could actually see that there's a network here. So each neuron has maybe thousands of synapses to some other neighboring neurons. And we know that the complex phenomenon involved in, well, the mind somehow emerges from the way these neurons interact with each other. But it's tricky to get a full understanding of this. You could make some sort of attempt by representing this as a network, taking into account that each neuron has some kind of membrane potential, which is affected by the action potentials that it receives from its neighbors, and constructing a simple model to see what that would give you. I want to consider each species to be a node, and when the species interact with each other, for example, one species eats another species, then we have a directed edge there. In a financial system, the nodes might be banks or other firms, and when they lend money to each other, that's an interaction. In many of these cases, what we really have is a dynamical system on a network, and we're interested in how the structure of the network can affect the kind of dynamics that we see. So here we have on the right, with the neural network on the right, we have the dynamics of a single neuron here. But here, for example, in the ecosystem, we see time series for two different species, so wolves and moose, which interact with each other. And you see they fluctuate quite a lot, and it's often quite random, but in some sense, this depends on how the network is connected. And of course, usually you have many more species than this. At the bottom, you have a time series from financial markets of some kind, not so different from the ecosystem at first glance. And this is the case for many complex systems. Thing to note here is that in all cases, the interactions are not necessarily symmetric. So the fact that neuron A sends a signal to neuron B doesn't mean that the opposite also can happen. Or if a species A preys on species B, it doesn't mean the opposite happens. So these would be represented by directed networks. Okay, so the late Robert May, who died very recently, unfortunately, looked at the problem of complex systems and wrote this very influential paper in the early 70s titled, "Will a Large Complex System Be Stable?" And what he showed is that all else being equal, if you take just an imaginary system, so a simple model of a complex system with some kind of dynamics on it, without knowing much about it, then in general, the larger the system, so the more elements it has, and the more complex in the sense that the more interactions between the elements, so the more edges in your network, the more the system should tend to be unstable. So any dynamics that you have on it is more likely to end up in certain elements sort of becoming larger and larger, and other ones becoming ever smaller till they disappear. And so the system somehow being unstable, the larger and more complex they are. And this was particularly shocking to ecologists, and it led to this long debate called the stability diversity, the stability diversity debate, also known as May's paradox. This is because in ecosystems, what we see is that the particularly large ecosystems, for example, the Amazonian rainforest or coral reef, are actually particularly stable in the sense that you don't see the whole thing just collapsing like you might see in your back garden if you try to make a few species interact with each other in a particular way. So ecologists have always assumed that the larger and the more complex, the more stable. And realizing that this didn't make sense mathematically was surprising, and people have worked on trying to understand what's special about ecosystems. In fact, Bob May suggested at the time that there must be something about ecosystems, something about the way they're structured probably, which leads to them being more stable than we would expect and becoming more stable with size and complexity. So a few years ago, I was thinking hard about this problem and wondering what could be special about ecosystems. So here you have a picture of a typical ecosystem. When we just take into account predation, like here, so the fact that one species eats another, we call this a food web. And there are many empirical food webs out there that ecologists have worked out by, for example, looking at different species and seeing what's in their stomachs. And something that immediately arises when you just think about it is that you have a kind of hierarchy of species. So at the bottom, you always have some kind of plant or the autotroph. And then you have some species that eat the plants, like the vegetarian ones, the herbivores. And then you have some carnivores that eat them, and maybe some other kinds of carnivores further up. And this is what ecologists refer to as trophic levels. Trophic just means, comes from eating in Greek. So it means something to do with eat. And it's these levels that emerge from the fact that different species have different diets. So here we'd have the level 1 is the plants, level 2 is the herbivores, level 3 is the primary carnivores, and so on. You can define that in terms of a network in this way. So you can just say the level of species I, I'm always going to use subindexes I, j, well, subindexes for different nodes in my system. So the level of the trophic level of species I is 1 plus the average trophic level of its prey. Okay, and this is represented with this part over here, because A is what's called the adjacency matrix. So my matrix A takes the value 1 when there is an edge from node J to node I. So for example, if over here 2 eats 1, that means that A sub 2, 1 has a 1, but 1 doesn't eat 2, so A sub 1, 2 is a 0. This is the trophic level of species J. And this is what's called I's in degree. So that's the number of edges that come into I. For example, again, if we take node 2, 2's in degree is 1 because it only receives 1 edge. Whereas, for example, 5 has in degree equal to 3 because it has 3 incoming edges. And likewise, you have an out degree, which is the number of edges that emerge from you to other species or to other nodes. So this is a simple equation. And you see that it doesn't necessarily give you an integer number. So for example, species 5 here has a fractional value. It ends up having 8/3. Species 7 has 32/9. You could get any fractional number there. So this is standard in ecology. But I wanted to measure to what extent are these levels fairly well defined. So this degree of order. And to do that, well, one way of doing it is to say, well, on each edge, I will measure a trophic difference, which is the difference between the level of the predator and the level of the prey. So Si minus Sj. So for example, to go back to this edge here, x2, 1 would be 1, for example. So the interesting thing about these x's is that if you look at the distribution of the x's over all the edges of the network, you get often some kind of Gaussian, but you get some kind of distribution, which is always has a mean equal to 1. That's by definition. It's quite easy to derive that from this expression. But the interesting thing for me is the variance in this distribution, or the standard deviation. So this standard deviation I call Q. It's just a parameter, or you can also call it an incoherence parameter. And this is what captures the degree of trophic coherence of your network. And I'll show you in a minute with some pictures why that is. But first, I'd like to point out that you can express this equation up here on the right as a matrix equation. So over here, we have this equation written as L applied to the vector of trophic levels equals another vector V, where L is this matrix down here, which depends on the adjacency matrix and on this vector V. And the V's are defined like this. It's just the maximum of the in degree or 1. Basically, what this means is for most nodes, it's the in degree. But when the node has integer equal to 0, well, then it's 1. I should have maybe mentioned when I gave you this equation at the top here for the trophic levels, that by convention, ecologists say that the trophic level of the basal nodes, so the ones that are at the bottom, are equal to 1. So when ki in equals 0, then we just define this as 1. That's a convention. You could define it, it might be more natural to mathematicians to call that 0, but it doesn't affect this definition of trophic levels and this definition of trophic coherence. It just displaces the trophic levels by a constant. Okay. And basal nodes are these ones that have ki in equal to 0. Okay. Here are a couple of different networks that we just generated artificially. And the one on the left is maximally coherent. So as you see, it fits into integer trophic levels. So all these are level 1, level 2, level 3, level 4. This means that all the trophic differences are equal to 1. So when you look at that distribution, it's just a Dirac delta centered at 1. This network over here is a bit more incoherent. You can see it's a bit more random. And some of the edges have a difference that's larger than 1. Some of them have a difference that's smaller than 1. And so you get this standard deviation 0.49. It turns out that we can, and I'll show you later how we do this, you can work out analytically what would be the expected trophic coherence if it was just a completely random graph with some basal nodes and compare it to that. So in this case, this expectation would be 2.24 for this particular network, which means that both of these are significantly more coherent than random. So even this network over here on the right, which looks a bit more jumbled up, is in fact more coherent than we would expect randomly. So this is the degree of order that I'm interested in here. How can we study this numerically? So how can we make networks like those ones with a given trophic coherence? Well, there are a couple of different versions of this model, but I'm going to show you the one that my first PhD student, Yanis Claes, came up with, that we published in this paper. And here what we do is we start with some number of nodes that we want to be the basal nodes. Say we want that to be 3. And then we add as many new nodes as we want. So we can set the number of nodes we want in our network in the following way. Each node enters the system and chooses randomly from among all the nodes in the system one to be its in neighbor. And it has just one edge to that in neighbor. So it could be any of them. So you do this up until you have n nodes. And then you notice that these nodes all have an integer trophic level at the moment. It's like a temporary trophic level. And then we use those temporary trophic levels to place more edges in the network with a probability that depends on their temporary trophic difference. So for every pair of nodes in this network, there is a trophic difference. For example, between this one and that one, it would be 2. And we realize as many edges as we want to, but with a probability such that it's more likely to take those that have difference 1 than those that have, say, difference 2 or difference 3. And we can set the distribution that we want for that. So let's say we take a Gaussian, we give it a standard deviation, and then we use that to decide which edges we place in here stochastically. So if this was a very peaked distribution, we would only realize edges that go from one trophic level to the next one up. So we would have a perfectly coherent network. If, however, we take a slightly broader distribution, we will get some other nodes as well, some other edges as well, some edges that may be longer or shorter than that, including self-edges if we want. And if that's the case, we have to then recalculate the actual trophic levels that emerge, which won't be the same as these integer ones. But this gives you a monotonous relationship between the parameter that we use here, so this standard deviation that we introduce as a parameter, and the trophic coherence that we then obtain. And it's a simple model to do some calculations with. So we can work out, for example, that in the coherent limit, these distributions are distributed as a Poisson, as you'd expect, actually. And you can set the number of nodes, the number of basal nodes, the number of edges, the number of basal edges if you want. Those are the edges connected to basal nodes. So it's quite handy. And then you can use these synthetic networks to study things if you want, numerically. For example, we looked at this paradox of maze. I'm not going to go into the details of this because it's not that relevant and it's a bit long. But essentially here, we were taking some different models that are out there in the literature for generating something that looks like a food web. So these are models the ecologists use to make artificial versions of food webs to study them. And so each of these different acronyms mean different food webs, different food web models. For example, this is the niche model that's very famous. This one up here is the cascade model. These are some other ones. And here what we do is we measure the degree of instability that network should have. This is essentially the largest eigenvalue of a Jacobian at an equilibrium point, but I won't go into the details of that. We just consider some dynamics and look at the stability of its equilibrium point. And here we simulate networks at different sizes. So this is the number of nodes, and the mean degree scales with the size. And this is what Bob May predicted, that this would tend to increase, so the networks become more unstable. This is another prediction that takes into account some more things. And this is what all these different food web models do. They all grow with size, so they all become more unstable with size, which was precisely the paradox. But when we do it with the model that I just showed you, or rather with its ancestor that was a little bit different to the one I showed you, but still captures trophic coherence, we find the following interesting result. When we take a large parameter t, that's the input parameter that I use to give me the trophic coherence. So that's basically the standard deviation of that initial Gaussian. The trophic coherence that we get isn't exactly the same as t, but it's monotonously related to it. When we use a high parameter, so we're making incoherent networks, well, then we get what we would expect for a random graph. We get that the instability increases with size. But as you reduce this parameter, so you make the networks more and more coherent, this slope drops until the point that it can actually become negative over some size. So we end up making the networks more and more stable by making them bigger. And we're not changing anything else about them. We're just generating networks as we're doing over here with a given number of nodes and number of edges. But with if we take this parameter to be low enough, we'll end up making them more and more stable with increasing size. So this on the face of it would seem to solve this paradox, although I must say this is only in this particular way of measuring stability, which is essentially Lyapunov stability. In ecology and in other areas of science, there are many different definitions of stability that people are interested in, and this all needs much further exploration to understand the relationship with stability in other contexts. But even in this simple context, you can see that it really matters how stability depends on size. Because, for instance, imagine you're in a world like the one on the left, where systems become more unstable with size. But if you have, for instance, an ecosystem, like a rainforest or something, and new species are always arriving, they might be immigrating from outside, they might be mutating into different species. As the system gets bigger, it will get more unstable. But at some point, you'll hit some kind of threshold where it can't be more unstable than that, because it will start losing species again. So one of the species will just become too unstable in the sense that it will just get bigger and bigger and eat everything else, or it will get smaller and smaller and go extinct. And when that happens, you lose some species, but then you revert to a more stable situation. So what we'd expect is to see the networks hovering around their sort of equilibrium point. And there are some models that simulate that. However, if we're in this kind of world, well, you might be stable, you might lose just a small number of species. But if that pushes you into this regime here, where you become unstable, you can't recover by losing more species. It actually gets worse. And so you might go through a tipping point such that you lose many, many more species before you become stable again. So knowing what kind of ecosystem we're in, or in general, if this is for complex systems in general, it might apply to financial networks or other systems, could be important for this kind of reason. Now, why does trophic coherence matter for stability in this way? So what it seems to come down to is feedback in the network. So for instance, here we have what's called a directed cycle. So what this node here does affects someone else, and that comes back and affects it again. So depending on if this feedback is positive or negative, this can be a stabilizing interaction or unstabilizing or destabilizing interaction. And so this is crucial for complex systems in general, whatever the dynamics happens to be. And so working with my colleague Nick Jones, we looked into how can we make a connection between the trophic coherence of a network and the extent of feedback that we'd see. And well, fortunately, this relation exists between the eigenvalues of the adjacency matrix and the trace of the powers of the adjacency matrix. Okay, so these are basically moments of the eigenspectrum. So when you have a matrix, you can plot its eigenvalues. For example, each of these correspond to different real-world networks, and I can get its eigenvalues. Then the complex plane, because if the network isn't symmetric, so if it isn't an undirected network, in general, your eigenvalues will be complex. However, they will be complex conjugates of each other. So you'll get something symmetric like this about the real axis. And there's plenty of information in these different eigenvalues about the network. Something that people look at a lot is the leading eigenvalue. So the one with the biggest real part, which is actually also the spectral radius, assuming that this is what's called a strongly connected network. So if your matrix is irreducible. So well, you can get various different things from here, but these eigenvalues reflect in some way the feedback here, and I'll show you this in a minute. So what this equation here shows us is that so these are averages over eigenvalues to some power. So in other words, those are moments of the distribution of eigenvalues. Can be calculated as the trace of the adjacency matrix to that power, because this in some sense represents the number of directed cycles. Okay, if you have an adjacency matrix, and we've said that you have an interaction from, say, node I to node j, then the element a, ji will be equal to 1, otherwise it will be 0. But if we have an element in, say, the adjacency matrix to the power of 3, what we're saying is that a path like this exists. If that element equals 2, it means that there are two paths like this. Okay, so that's the useful thing about these powers of adjacency matrix. And of course, the trace is invariant to a change in base, and that's why this always holds. It holds in the bases in which the matrix is diagonal, and in every other basis as well. Okay, so using that, what can we do? Well, I'm going to show you some general results for networks, or graphs. So often we'll just consider a graph, so we call it J. So G of NL means some graph with n nodes and L edges. The mean degree, so again, these little brackets I use here just mean average over nodes. So the mean degree is this L over n. Then we can look at the number of basal nodes. As I said, those are the ones with in degree equal to 0. The number of basal edges, those are the edges that emerge from the basal nodes. This is something that crops up a lot. It's called the branching factor. So this is this correlation between in and out degrees. If there's no correlation, then the branching factor just equals the mean degree, but otherwise it could be a bit smaller, a bit bigger. And then we can measure things like the number of paths between nodes, well, the total number of paths between nodes which have length nu. So a path being, we start at one node, we follow these directed edges all the way to some other node. So that's calculated like this. We can look at the number of paths which are cycles, so the ones that come back to where they started. they're not the simple cycles that people are often interested in graph theory, where you don't repeat edges or nodes. Here you can repeat yourself. But if you think of all the paths that simply come back to where they started, we can calculate it, as I said before, either with the trace of this matrix or with the eigenspectrum. And now I'm going to talk about what are called ensembles. So this is something we use a lot in statistical physics. It's basically when you think about a whole set of possible entities that meet some constraints. So for example, you might say, I'm going to think about all the graphs which have a given in and out degree sequence. So say I've got some nodes, and I want them each to have a particular in degree and a particular out degree. And I'm going to think about all the possible networks that could respect those sequences. For example, that would be one such network, but there would be many more. And can I do some statistics with what I expect to emerge just given that constraint? So this is called the configuration ensemble. And in the configuration ensemble, we can work something out. So we can say, well, the expected value of the adjacency matrix has that form there. So it depends on the in and out degree. That's the, in some sense, the probability that there will be an edge between these two nodes. Here I'm making the assumption that these degrees are never extremely large, never of the size of the system. Otherwise, this needs a correction. And you can, using that adjacency matrix, so using that expectation for the adjacency matrix, you can just plug that into these equations down here, and you can get, for example, the number of paths of length nu. So this is the expected number of paths of length nu in the configuration ensemble, the alpha to the power of nu. In some sense, what that means is that if I draw lots and lots of networks from this ensemble, so I make lots of networks that simply respect those degree sequences, and in each of them I measure some property, like in this case, the number of paths of length nu, then this is the mean value I will get. And the more I draw, the smaller the variance, and eventually they will all have, if I do it infinite times, this will be the mean value. I'm using these symbols to denote expectation. So expectation in the sense that it's the mean value over all these draws from the ensemble. So for the configuration ensemble, I'll use these little hats, these tildes. No, not tildes, what they called, well, little hats, let's call them, little triangles. I can also work out the number of, so the M was the number of paths that come back to the origin, so the number of cycles. This is the number of paths that don't necessarily come back to the origin. Now, it's another ensemble I'm going to look at. This is the basal ensemble. So here we said, let's consider the directed configuration ensemble with one extra constraint, which is that every non-basal vertex is another word for node, so every non-basal node has an equal proportion of basal nodes, which is just this over here. Okay, so if you're not a basal node, then you have some proportion of edges that come from the basal nodes and some proportion from the non-basal nodes, and that's the same for all non-basal nodes. This ensemble is actually equivalent to the configuration ensemble in this limit here. So it doesn't make too much difference if the networks are very large. So these networks will look like something like this. We just distinguish between the basal nodes and the non-basal nodes, which are all basically identical as far as trophic levels are concerned. And now the expectations in this ensemble I'm denoting with a tilde. So this, for instance, is the expected mean trophic level. So the average trophic level in a network with B basal nodes, N nodes, L edges, L basal edges will be this. I can also work out the expectation for the trophic coherence. It has this simple form here, which just depends on the number of edges, L and basal edges. I can also work out the expectation for the branching factor. And with these things, I can find, for example, the proportion of paths in my network, which are cycles. So the proportion of those paths that come back to where they started, which has this form over here. Okay, and now I'm going to show you just one more ensemble. I promise this is the last ensemble, called the coherence ensemble. So this is like the directed configuration ensemble as well, but now we've fixed the trophic coherence. So I'm saying I want to consider all the possible networks that not only have a given degree sequence that I can impose, but they also have a specific trophic coherence. So I can try to understand the effect of this trophic coherence statistically. So why do I do this? Well, let's think about this network here. I want to understand the effect of feedback in these networks. So essentially, this comes down to saying, if I take a network and I just consider some path through the network, so just a randomly chosen path of all the different possible paths through this network, what is the probability that it will be a cycle? So I want to know how many of these paths actually come back to where they started. So I can take that problem and think about it in trophic level space, if you like. So I just project these nodes. Hi there, I can hear someone. That may be a good question, but I couldn't quite make it out. So we project these nodes onto this these trophic heights. And the question I just asked, so is a randomly chosen path a cycle, is equivalent to saying, if I take a random walk on this one dimension, do I come back to where I started after some number of hops? And this random walk, the size of the hops will be drawn from my distribution of trophic differences. So if this is a very peaked distribution, so most of the differences are equal to 1, so it's a very coherent network, you can see that you never really come back. You just keep hopping up and up and up. Whereas if it's broader, then you become more likely to come back again. So you can actually work that out. You can say this S is the length of my random walk. So it's the number of hops in my walk over these different hops K. So these X's are the trophic differences I showed you before. And this S will of course follow by the central limit theorem, it will be Gaussian distributed. It might actually be Gaussian distributed anyway if this is a Gaussian. If it's not a Gaussian, then the longer the path, the more it will look like a Gaussian because of the central limit theorem with this mean and this variance. Nu, I remind you, is the number of hops in my path. And so I can see how likely that S is to be 0, which gives me the proportion of paths which are cycles. It has an expression like this just from the fact that it's a Gaussian. And then using the Basel ensemble to sort of ground this, because we have a parameter here that we don't in principle know what it is, but we can take the Basel ensemble case to obtain that parameter. Then we see that the proportion of paths which are cycles has this form here. So it depends on some of these expectations I worked out before. It depends on the trophic coherence here and here. And it depends, of course, on the length of the cycles we're interested in. Okay, I'm going to use that proportion. So just to remind you, this is an expectation in this coherence ensemble. So in the coherence ensemble, I'm using a bar to represent expectation. And so this is the last ensemble I've shown you. So this is the bar for the coherence and these for the Basel. Those are the only ones we're going to see now. What can we do with this? Well, you can work things out. Like, for example, the expected number of cycles would be something like this. So it's an exponential in e to the nu, where nu is the length of cycle. And this parameter tau is something that we call a loop exponent. And I'll go back to it in a minute, but it's a parameter that appears in the exponent here. And you can work out other things. You can work out, for example, the expectation for the moments of the eigenspectrum. Again, we have this e to the tau nu. We can take this limit, if we want, using this expression, and find that the spectral radius, or the eigenvalue with the largest real part, is e to the power of tau. So it's very simple. We can work out the probability that a given network will be acyclic. So there will, in fact, be no directed cycles at all. This also depends on this exponent tau here. Now, you notice that everything depends on this exponent tau. And so let's look at this. Here we have this branching factor, which will tend to be more or less the mean degree, perhaps a bit more, a bit less, depending on the correlations. So this will tend to be, the logarithm of this will probably be larger than 0 as long as the mean degree is larger than 1, which is most networks. Over here, we have this difference between the inverse of the variances here. So this is the what's it called? The basal ensemble trophic coherence, and this is the actual trophic coherence that we've set in our coherence ensemble. And what you notice is that this parameter here, if the network has the coherence that we'd expect randomly, so it has the basal ensemble coherence, then these two cancel, and we're basically left with the fact that this is just the log of alpha. But that's not always the case. So when those two cancel, we get a tau that's greater than 0, and in this case, all these different exponentials are increasing. So we're going to have, for example, that the number of cycles of length nu will get bigger and bigger with greater nu. So the bigger the length, the more we're going to see. This is what happens when the Q is relatively high, so it's more incoherent. But there will always come a critical Q below which this tau becomes less than 0. So whatever your alpha and whatever your Q tilde is. So when they're sufficiently coherent, these networks, then you have a negative tau. What that means is that expressions like this decay exponentially instead of growing exponentially. So for instance, the number of cycles of length nu will now decay with length. So you might see a few cycles of length 2, even a few of length 3, and as you go to longer lengths, you just don't see any anymore. So you can see that this is a very different regime of feedback than one in which the number of cycles grows exponentially with size. And all those other expressions will have very different values depending on tau. So that was for this invention of ours, which is the coherence ensemble. But how do real networks look? Do they fit at all with these expectations? Well, here we've taken some real networks out there from the literature. Food webs, gene regulatory networks, metabolic networks, neural networks, some other various miscellaneous different kinds of networks. And we've plotted, for example, this leading eigenvalue. So this is actually the spectral radius of these networks against this parameter tau. And what we see, so this black line is the exponential that I showed you before. So that's the expectation in the coherence ensemble. And these symbols represent the actual values for these networks. And what we see is that most of them fall quite closely onto this line. So we do, in fact, see this separation of these two phases. We have a regime where the leading eigenvalue has some value, which will be more or less like the mean degree. But we have some other ones where it's vanishing. Now, this wouldn't be understandable without taking into account trophic coherence. Some of these networks are quite dense. We'd expect them to have large leading eigenvalues, and yet their eigenvalues are 0. So all these eigenvalues collapse onto 0. And so the explanation for this is the fact that they are quite trophically coherent, and this suppresses the feedback and hence collapses these eigenvalues. We can do the same over here. We can look at which of these networks have cycles and which ones don't. In principle, we'd expect all of these networks to have cycles if they were just similar to random graphs. But what we see is that all the ones that are above most of the ones that are above this limiting difference between these trophic coherences are acyclic. So all the blue ones are acyclic graphs. Again, there's no explanation for why all these networks would be acyclic. If we just looked at their density, it doesn't make sense. And people have suggested other functional explanations for why there may be less feedback in these systems. But really, if you take into account the trophic coherence, that's enough to explain it. So this seems to describe real networks to some extent. Now, what other effects might trophic coherence have then on complex systems? So we've looked at various different cases, for instance, contact processes, so which in some sense describe epidemics, like the ones we're all becoming uncomfortably familiar with at the moment, and how these spread. And we find that trophic coherence can make the difference between whether an epidemic will spread through a directed network or not. And if it does, whether it will become endemic and just stay there forever or peter out. Other things like, for instance, this property of networks, especially in food webs that people have been interested in, called intervallity, which is the possibility of of putting all of a given species diet on sort of one continuous interval, which is thought to be something important in the structure of food webs, this actually also emerges from trophic coherence. Motif distributions. So motifs in networks are these little subgraphs. So you say, for example, for every 3 nodes, what possible kinds of subgraphs might there be there? And we just count how many we get of each of these different types. And we compare that to some null model, so basically to a randomization of the network. And it's been found that there are interesting signals here. So different kinds of networks have different sorts of profiles that represent sort of families of networks. And we found that, at least looking at food webs, this also seems to come down to trophic coherence. So just getting the trophic coherence right, we more or less know the profile that these networks will have. And then you can use trophic levels for other things, like, for example, to say something about the function of the nodes in your network. So we know that in an ecosystem, the trophic level tells us whether a node, whether a species is, say, a herbivore or a primary carnivore or an apex predator or whatever it may be. Can we do the same in other networks? So I don't know if you're familiar with this masterpiece of Dr. Seuss's called Green Eggs and Ham. It's a great book. It only has 50 words. And here I've simply drawn the network of word adjacencies. So whenever within one sentence, one word was followed by another one, I've drawn an arrow between them. So here you can get the sentences in the book by following these arrows. I do not like them, Sam I am, I would not, could not, on a boat, or that kind of thing. And not every path in this network is a grammatically correct sentence, because language isn't Markovian, but the sentences in the book can be found as paths in here. The interesting thing is, well, I should say that the trophic levels here are calculated on the transpose of the adjacency matrix here, so they go up against the direction of the arrows that I've drawn. The trophic levels here give you some information about the syntactic function of the nodes. So, for example, the nouns are these blue ones. They're mostly down here, and except this proper noun up here, which is Sam, just like me. So most of them are down here, and so the average trophic level of the nouns is low, whereas the verbs, the red ones, are much higher up. And I've represented other things with other colors. So, for example, adverbs and pronouns, adjectives. So this means that just looking at the trophic levels of a system like this can tell us something about the functions of those nodes. And this is presumably similar in other networks, for example, in gene regulatory networks, which in some sense are a bit like a grammatical network as well, or other things. So that's an avenue that we're still exploring, understanding what we can say about what an element in a complex system does as a function of its trophic level. And this leads to a new way of plotting networks. So this is the standard way of plotting networks in ecology, but not usually in other areas. So this is a food web from Ethan Estuary. And here we just plot the nodes according to their trophic level, represented on the left here. So this is what an ecologist would usually do, so that they can see that these are the plants, these are the herbivores, these are some carnivores. If you plot it the way people often plot networks with some algorithm based on trying to minimize how much each edge is stretched, well, you get something like this. These algorithms are good at showing you community structure, but they don't in any way reflect trophic levels. But we could do this with all networks. So in this particular network, for example, we can look at the
webcam, integrated webcam.
Oh, sorry, am I running out of time?
രണ്ടും ചോദിക്കും, ക്യാമിൻ്റെതും ഓഡിയോൻ്റെതും ചോദിക്കും. ഇതിപ്പോ പറഞ്ഞ പോലെ.
So, sorry, I didn't get any of that. So this is the trophic coherence for this particular network, and we can compare it to its Bayesian ensemble expectation. So that's a way of saying how much more coherent is this network than we would expect. It would be 1 if it was just a random network, but it's quite a lot smaller, so it's quite coherent. And this gives us this tau that's negative. But we could do the same for other networks. For example, this is the neural network of the worm C. elegans. This is the only fully plotted neural network that we have. And here again, we could see the different trophic levels of these nodes. These down here would be sensory neurons, where the information comes into the system, it travels through these different kinds of neurons, and it ends in these motor neurons. If we'd plotted it like this, like people tend to do, it doesn't really give you any of that information. You need to plot the trophic levels to see this. Again, here we can see this network is also more coherent than the random expectation, but its tau is nevertheless positive, so it's in a different regime. And something else that these pictures tell you is what's called the strongly connected component. So in a weakly connected network, so a network in which you can reach, if you ignore the directions, then you can get from one node to every other node. You can nevertheless think about whether it's strongly connected. A strongly connected network means a network in which you can reach every node from every other node along a path respecting the directions. If it's not entirely strongly connected, there may be a strongly connected component. In this network here, there's the largest strongly connected component has only 2 nodes. Whereas in this one, so those are the diamonds, all the rest are circles. Whereas in the C. elegans network, all these diamonds are part of the strongly connected component. So the strongly connected component is much larger. So that's the subset of nodes that can reach each other by directed paths. And so I might go over some of this quickly because I think I'm maybe running out of time. But something I've looked at in this recent paper that's just appeared, I think last week, is strong connectivity. So just as we did with other properties like the spectral radius, we can look at the fraction of nodes which belong to the strongly connected component as a function of tau. And we see that real networks have these 2 different phases, one in which there is a strongly connected component that's sizable, one in which it's negligible. And using those preferential praying model networks, we can see that there's a phase transition with trophic coherence between a phase with no strongly connected component and the big one. Another property is that's related to trophic coherence is called non-normality. Again, I won't go into the details of this, but a network is said to be normal if it commutes with its transpose. So if A times A transpose equals A transpose times A, then it's normal, which is what you'd get if the network was undirected, say, because if the network is symmetric, this would be the same by definition. If it's directed, then it could deviate from normality. In fact, we probably expect it to deviate from normality. And in this recent paper, these people showed that real networks are very significantly non-normal, or many of them are anyway. So I won't go into these things too much, but this is what you can use to measure the deviation from non-normality, where this is the Frobenius norm, and these are the eigenvalues, and this is the normalized version of Henry C's deviation from normality, which lives between 0 and 1. If it's 0, the network is normal. If it's 1, it's completely non-normal, and it could be anywhere in between. And so what I showed in this paper is that the expected deviation from normality for digraphs drawn from the coherence ensemble tends to 1 with increasing trophic coherence. So the more coherent, the more non-normal. And in fact, you can put a bound on non-normality as a function of the mean degree. So there's a little proof of that, but I won't go into it, which essentially you just put bounds on the sum over the eigenvalues using our expectations from the coherence ensemble, and you get that result. So in other words, trophic coherence leads networks to be very non-normal. And non-normality is an indication that there's some kind of global direction in the network. There's a difference between sort of going upwards and downwards, if you like. Again, you look at some real networks, you can measure this deviation from normality, and we find the same kind of thing. As we go towards a negative tau, they suddenly become very non-normal, and in fact have non-normality equal to 1. These are these theoretical predictions, so bounds actually. And last, I want to show you this effect on a dynamical system. So let's take again that simple neural network of this C. elegans worm, and let's do the following naive thing. Let's just put a model of a neural network, so a model of how we expect neurons might interact with each other on this same network. So this is called a Hopfield model, and we just assume that every neuron can either be firing or not firing, so it has two states, and they receive an input from all their neighboring nodes, and that can make them either fire in the next step or not fire, depending on if it's a positive or negative sum. We can use the edge weight to encode some patterns of activity, as if you took some images, for example, with pixels. You could embed them using what's called the Hebb rule, and then the minima of the dynamics would become the patterns and their negatives, the anti-patterns. Here I've done the simplest thing. I've just put one pattern on the network. So we just have two minima, the pattern and its anti-pattern. And let's see what the network does. Well, this is what we expect actually for a random graph, which is that this magnitude which measures which pattern are we looking at goes to either to -1 or to 1. In this case, it's gone to -1, and it just stays there. So it's a Monte Carlo simulation where it just goes to -1 and it basically hovers around there. It's just retrieved that one pattern. But that's not what we see on the actual neural network. This is what we see when we randomize the edges. So we take the edges and switch them many, many times so that we destroy all information apart from the degree sequence. When we do it on the actual network of the worm, we see something very different. We see that it basically hops between these two patterns of activity, between these two memory patterns in this strange way. So why that must be something to do with trophic coherence, because it's the only thing that we know of that we haven't changed. So this is another test that we can do, which was basically we show it one of the two patterns. So we take just the basal nodes, which are the sensory neurons, and we put those ones in either the pattern or the anti-pattern. It's a bit like showing the network some information. And what we'd like it to do is respond to the information, so change its state and go to the pattern that we've shown it. Now, the actual neural network of the worm does it much better than the randomized version of the same network. So the randomized version doesn't change its state hardly at all, whereas the other one does change its state in response to the signals. And here we explore the possibility that it's because of trophic coherence. So when we take an incoherent network generated with that preferential pairing model, we get what I just showed you before, that the pattern is completely stable. When it's coherent, showed here in purple, then it's completely unstable. It just hops about in this sort of Poisson process. But there's an intermediary level of coherence, which you could call the Goldilocks coherence, because you're in the nice sweet spot here, where you get the same kind of thing that we see in the worm's case. So we get this bistable hopping between the two minima of the energy here. So this is what looks more like the empirical case. The same for that test where I show it a pattern. So if I show the coherent pattern and the signal of a new pattern, so the coherent network a new pattern, it kind of sees it, so it responds, but it immediately reverts to some random state. So it doesn't really function very well. Again, the incoherent network can't do it because it's not sensitive to the signal. But the Goldilocks coherent network does respond well. So it goes to whichever pattern I showed it, and it stays there for a little bit. You can do this with more patterns. So a real neural network that was any use would maybe have many different patterns. Here I've just put 4 on the networks to give the idea. So each color in this time series represents one of the patterns, and we look at the activity of each pattern. So whichever one is close to 1, that's the one that's being represented in some sense by the network. And underneath, I show you which of the patterns is being shown to the basal nodes. Again, in the coherence network, it doesn't do it very well. It's sensitive, but it immediately loses the pattern. In the incoherent one underneath, it just goes to in this case, the green pattern, and it doesn't matter which one you show it, it never goes there. It just stays stubbornly in the green pattern. But in the Goldilocks network, so an intermediate level of trophic coherence, it does the task well. So it goes to the pattern and it keeps it for as long as you don't show it another pattern, which is what we'd hope it to do in this task. So you can measure its performance as a function of traffic coherence, and you always have this sweet spot of performance of that particular task, which is somewhere between a Q equals 1 and 2. And we can understand to some extent why this happens by thinking again about this Basel ensemble. In the Basel ensemble, you can work out the probability that the state of the system will flip, and under mean field approximation, and you get this expression here, which depends on this incomplete beta function, which is a function of these Qs. And this allows you to find the critical Q, which is equal to 1, at which the probability of flipping starts becoming smaller. So this is just done for the Basel ensemble, but you can infer from this that in all networks we would have a critical Q around about 1, and that is what happens when we do simulations. So essentially you go from a network where it's flipping all the time to one where it doesn't flip so much, and then eventually it flips very infrequently. And so we see that there's an interesting sort of transition around this Q, which is where the network is sensitive but does the task well. So this is interesting because in people who study neural networks basically think of two different kinds of neural networks. They're recurrent neural networks, where all nodes can connect to all other nodes. And this is usually what's also used in neuroscience to model the brain. And those networks are fully incoherent. They're random, or even sometimes complete. Then we have these coherent networks, and in artificial intelligence these days, people use deep neural networks a lot, which the general structure of a deep neural network is networks with many layers, which are maximally coherent. But what we're saying is that there may be a different architecture in between these two things, which is in some sense better than either a recurrent network or a deep neural network. In fact, it allows us to interpolate between these two architectures. So this is something I'm studying at the moment to understand what advantages can we get in AI from using a somewhat incoherent architecture. And finally, I just want to mention quickly that my colleague Robert Mackay recently came up with another definition of trophic levels, which has many advantages over the ones I've been using, and yet preserves many of the things I've said. So he said, instead of defining the trophic levels and then using those levels we calculate the coherence, why don't we define the levels as those which minimize the incoherence? So this is a function that sort of describes the incoherence. We look for the levels, I'm calling them H now, to distinguish them from my other levels, that minimize that. And we find that we can express this with an equation which is very similar to the one I showed you before. The main difference being that it's now symmetric. So where before I just had A, now I have A and A transpose. Where I just had the diag of K in, I have K in plus K out. So this is the Laplacian of the symmetrized adjacency matrix. And this is what's called the imbalance vector, the difference between the in and out degrees. When you solve this equation, and you see you can solve this equation for any network, it doesn't have to have Basel nodes now, the way the other one did. You get some trophic levels, you can measure the trophic coherence, and essentially we find that these trophic levels are very similar to the ones that we would find anyway if they are Basel nodes. But this approach allows us to extend to all networks. So it has various advantages of not needing Basel nodes. It has this symmetry. When you invert the direction of the edges, we still get the same inverted levels. We can get a measure of incoherence which lives between 0 and 1, so it's bounded. And for maximally coherent networks, they both coincide. I'm just going to end with some pictures of networks. So this is some different food webs. Underneath, we have the standard trophic levels. So this is a more coherent network. This one on the right is more incoherent. And when we use these symmetrized trophic levels, you can see that it's somewhat similar. But the Basel nodes don't have to be necessarily Basel. They have different values. You can use this now for other networks. So here, some of these networks, we wouldn't have been able to measure the levels with the standard definition because there are no Basel nodes. But in this case, we can. So here's two different social networks, one in a high school, one in a prison. Here's some networks of international trade. And you can see that we can use these things to look at the functions of these nodes in some sense. So where are you in an international trade network? Are you more of a producer of prime materials, or are you a manufacturing economy, or some kind of economy that basically consumes them? Some more examples. So this is a neural network from a rhesus monkey. And these are one of these networks of epilepsy patients of electrodes on their brain. And just to finalize, these symmetrized trophic levels seem to preserve the other things that I was talking about before. So you can still work out things like the spectral radius of your adjacency matrix as a function of this tau, and all the other things I talked about. So this is quite exciting because it allows us to study these things in all networks now. So just to conclude, I've said that directionality is a key ingredient of complex systems. So we can't just ignore it and pretend that an undirected network is a good description. We get these two regimes, the loopful and the loopless regime, which have qualitatively different topological and dynamical properties. So it's particularly important to know which regime you're in if you've got one of these networks and you want to know, for example, will an epidemic spread? How will some other model, like a neural network model, behave? We've presented a numerical method which allows you to study these things in silico. That's a preferential priming model. And a mathematical tool called the coherence ensemble, well, together with some of the other ensembles I mentioned, which are useful tools for studying networks and understanding the importance of trophic coherence. We've shown that trophic levels can reveal something about the functionality of nodes. There are some interesting effects, particularly in the case of neural networks where you consider directionality. And this leads to all kinds of questions, like, for example, what does it mean for biological neural networks? Can we use this in artificial neural networks? And these are my colleagues that helped me in various different parts of this work. So Miguel Ángel Muñoz in Granada, Virginia Domínguez is now in Montpellier, Luca Donetti, who never sends me a picture, so this is the best I found, is also in Granada. And that's the group I started this off with. Then Yanis Claes is my first PhD student, who is now making a lot of money in London, I think. Nick Jones, who was my supervisor at Imperial College and at Oxford. Robert Mackay, who used to be my boss at Warwick, and Basil Sansom, who's working with us now, also at Warwick. So thank you very much for your attention. And please let me know if you have any questions.
Thank you, sir. So before we open the floor for queries, with your permission, please can I go ahead and introduce you to the gathering, because I was eagerly waiting to introduce, but due to some technical issues, I was not able to.
Oh, sorry, of course, thank you. Thank you.
So yeah, mathematics may not teach us how to add love or minus hate, but it gives us every reason to hope that every problem has a solution. And mathematics lecturers are the ones who teach us that and gives us that hope. And one such amazing lecturer is our speaker for today, Dr. Samuel Johnson. Dr. Samuel Johnson is a lecturer in applied mathematics at the University of Birmingham in the UK. He is also a Turing Fellow at the Alan Turing Institute in London. Dr. Samuel Johnson's research mainly focuses on complex systems, and in particular between network topology and dynamics. He is very much interested in topics related to neuroscience, artificial intelligence, ecology, and economics. He completed his studies on physics and mathematics at the University of Granada, Spain. He did his PhD on the topic interplay between network topology and dynamics in neural systems, supervised by Jeppe Torres and Jakin Marrow, and graduated in 2011. Dr. Samuel Johnson is a postgraduate from the University of Oxford before taking up a Marie Curie Research Fellowship at Imperial College London. So thank you so much for accepting our invitation in very such short notice, and SNS College is very proud to have had you with us today.
Thank you very much for having me. It was a pleasure was all mine, and I hope that next time it can be in physically as well as virtually.
Yes, sir, we're hoping to. Dear participants, the floor is open for queries. If you want to ask any queries, you can go ahead and post in the chat box.